All right, now that we've kind of dealt with converting coordinates and equations to rectangular to polar and polar to rectangular, and we're getting a little bit more familiar with the polar coordinate system, let's look at some different graphs you can have. Now, I'm not going to make you don't have to graph these by hand. I'm really just going to give you a picture and can you identify them either by equation or by name. Nothing crazy, nothing high level. So we're going to start with one of the most basic shapes there is on the polar system. Wow, I can't talk today. The polar coordinate system. Let's look at a circle. So here I have my polar graph, and I'm going to pop a circle onto it. All right, so I've got a circle now on my polar graph. Now, the equation to this polar graph is going to be, this one is r equals 3 cosine theta. 3 means I'm starting from the pole and I'm going out 3 units. So the radius is actually 1.5, but the diameter is 3. Cosine is simply because right here it's along the x-axis. If it was sine, it would be along the y-axis. So these are fairly straightforward. If you just have a number in cosine theta and a number in sine theta, that's going to be a circle. Very, very straightforward. A sine, the sine one will look like this. This equation is r equals 4 sine theta. And you can see the orientation is along the y-axis because sine is your y. The diameter is 4, so the radius of the circle is actually 2. So those are circles, and this is what it looks like on the polar system. These are equations of circles. These are the graphs. Fairly straightforward. So let's look at another graph. All right, so another graph that I want to actually be able to identify is called a cardioid. The way that it's easy to remember is it looks like a heart, but you can get these kind of confused with what we call limicons, limicons, dimpled limicon. So you want to show you the difference between them. In the formulas, a cardioid, your first number and the number in front of your sign is always got to be greater than 0. Now it could be a plus or minus, but these numbers, if this is a 4, this has to be a 4 to be a cardioid. That's it. If these two numbers are the same and you have a sine or cosine, it's a cardioid. The way that graph actually looks, it looks like a heart. It kind of comes into a cusp and comes out, and then in at a cusp and then comes out, and that's a cardioid. In fact, the equation of this is oriented along the sine is 3, my r equals 3 minus 3 sine theta. These numbers have to be the same. If they're the same, it's a cardioid. If it's not, it's going to be something else. So let's look at another. All right, so now what we're going to look at is actually called limicons. There's going to be 2 categories I'm concerned about, a dimpled limicon or a limicon with an inner loop. So we're going to look at the dimpled limicon first. If you notice, the equation's a lot like the cardioid, except now I have an A and a B instead of an A and an A. So what that means is these are going to be different numbers. If they are the exact same numbers as a cardioid, if they're different numbers, you just have to figure out, is it going to have an inner loop or is it going to be a dimpled limicon? So the way we're going to be able to tell is this inequality. Well, my A is going to be my biggest number. So if my number without the trig function in front is the bigger number, that is going to be a dimpled limicon. And what that actually looks like is this, where it kind of looks like a cardioid, but it doesn't have that really defined little sharp point. So the equation of this one is 3 plus 2, and because I'm along the x-axis, of course, that's going to be cosine theta, and that's r equals. So that's the equation of the actual dimpled limicon I have here. So now let's look at an example of a limicon with an inner loop as another example of a polar graph. All right, so a limicon with an inner loop. It's really the same formula as the dimpled limicon as the cardioid. The cardioid, if you remember, these two numbers have to be the same. In the dimpled limicon, your first number without the trig function is the larger number, and that's going to give you a dimpled limicon. A limicon with an inner loop, this b right here is going to be a much larger number. Or not much, it's just a larger number in general. It's going to have an inner loop. And the way that will look will be, where is it? Guess I should have way up here. So as you can see here, it's still a limicon, but this time it actually kind of loops all the way through. So with this equation, all I did was switch the numbers. R equals, well, my A's got to be my smaller number, so I've got 2, and this one is along the x-axis, and I did plus 3 cosine theta. That's the equation of the graph that's up on the board right now. Fairly straightforward to be able to identify this. If your B is the larger of the two numbers, it's going to have an inner loop. If your A is larger than your B, it is a dimpled limicon. And if your A and your B are exactly the same number, then that's a cardioid. So let's look at another example of a different type of graph that you can actually get with a polar coordinate system. All right, another one we have is called a lemniscate. A lemniscate is the only one that's going to have an r squared in front of it. You're going to have just a number here. If I ask you what a is, you're actually going to take the square root of it because it's always not. It's never going to be written as 2 squared. It'd always be written as 4. And then you have a 2 theta. What this graph actually looks like, kind of looks like an infinity symbol. That's a lemniscate. That's really all you need to know on this one. This one's pretty straightforward because it's the only one that's an r squared. If you see an r squared, it's just got the 2 sides, and that's it. We use this in math a lot to write infinity, I can tell you that much, but that's a lemniscate. Let's look at a rose curve. All right, so let's talk about a rose curve. Rose curves are quite unique when it comes to these graphs, and they're going to behave a little differently. If you notice here, there's no longer just a theta or a 2. This could be 3, 4, 5, 6, 7, 8, 9, 10. It's going to go up really forever. I want to just go ahead and tell you k is actually going to be greater than 2, and k is an element of my natural number. So 2 is going to be greater than 2. So 3, 4, 5, 6, 7. So starting at 3. All right. Now with this, when we have odds and evens, it behaves differently. So what I'm going to do is I'm going to show you 2 different odd rose curves and kind of tell you generically what every time k is an odd number, what actually happens. So the first one I want to show you is, where do I have it? Got to be able to see the whole thing. So here's the first one I have. If you notice, the equation of this one is going to be r equals 3 sine of 3 theta. And if you count the number of petals on this curve, there's 3 petals on this curve. The next one I'm going to show you is going to be r equals 3 sine of, I want to say it's 5 theta. 5 theta. So let me click this one off, and here is the one with r equals 5. Well, if you count the number of petals on here, you have exactly 5 petals. Well, this is always going to hold true for anything that's when this is an odd number. So when your k is odd, your number of petals is k. Now let's look at a scenario when k is even. So greater than 2, so 4, right? So let's go greater than or equal to 2. So let's take a look at that in the even situation. So here is the graph of r equals 3 sine of 2 theta. All right, count how many petals there are. There are 4 petals. Let's keep that in mind. What's the relationship between 2 and 4? Well, I can either add 2 or I can multiply by 2 to get to 4. So it's either going to be, I'm going to add 2 petals each time to the number, or I'm going to multiply the number by 2 each time. So let's look at a different one. Let's jump to 4. Let me find it here. And here is 4. Well, if I count the number of petals on the 4, well, I have 8 petals. So so for r equals 3 sine of 4 theta, I had 8 petals. So now when k is even, I want to do 2 times my number, 2 times my k. So if it's sine of 3, 2 theta, I know I'm going to have 4 petals. If it's 4 theta, I know I'm going to have 8 petals because of the 4. If it's 16 theta, I know I'm going to have 32 petals because 16 times 2 is 32. So these are the rose curves. These are fairly straightforward. You're not going to mistake them with other ones. It's just a matter of how many petals you have. Is it going to be an even or an odd? So let's look at one last one, which is kind of unique and is something you probably have drawn many, many times in your life. All right, so the last thing I want to show you, and you won't see this on the study guides or anything else, is just kind of a little extra, because I think this is kind of a neat little thing for y'all to see, something that you've done over and over and over again in your life. I'm going to give you an equation, R equals theta. That means as theta increases, as I'm going around, my R is increasing. Well, this is a spiral. And if I just graph it, you can see, and I'm going to zoom out on this, you can see it just makes a spiral. This is R equals theta. You've drawn spirals pretty much your entire life, but this is the mathematical equation to an actual spiral. And it's a fairly straightforward equation. I really like the R equals theta. It's just kind of a neat little thing to actually see. But those are all the different graphs you're going to have to know for this section in polar. And really, you don't have to know how to graph them or anything along those lines. You just need to be able to identify them from an equation, from a graph, and be able to name them. That's all you're going to have to be able to do. Hi, I'm Mr. Buzzer, and these videos are supplemental instruction for my students. If you found the video enjoyable, make sure you click the like button and click subscribe, as well as the bell for notifications to receive future videos on high school mathematics.